In this video, we will discuss a couple other things that can be done with a given power series, and in particular, we'll talk about how to create a new power series from an existing one. But first, let's recall that we have an object which we refer to as a power series that has the following appearance. So this will be a power series centered at C, and when at certain values on some interval that we call interval of convergence, so where x belongs to that interval of convergence, a power series may act like a function, and on that interval the following equation holds true, and we can use the following language. We can say this function is the limit of this power series, or on the other hand, we can say that this power series is a representation of that function. And one of the examples of such relation is a well-known identity now, that 1 over 1 minus x is equal to this power series, and all of this only makes sense when absolute value of x is less than 1. So in general, the question that we want to try to answer, there are two such questions that we want to answer. We want to see if, given a function, can we figure out the power series that represents that function. And question number two that we want to answer is, given a power series, what function is the limit of that power series, if such function exists at all. And if it does, so if we were able to, for some function, find the power series, or for some power series find a function, the question then would be, what is the interval of convergence? So we wouldn't expect for this statement to hold for all values of x, right? So these are the kind of the types of questions that we are interested in answering. And the first group of exercises that we'll be able to do is all going to be about using this identity. And it is really important to be comfortable with remembering this identity, as it would be considered one of the most basic ones. And as we progress, we will learn some other identities that you may choose to remember as well, or you may choose to remember the way it was derived. But the idea here is very simple. So if we take this identity mathematically, it seems very reasonable and natural for this identity to hold for anything that I throw in there instead of x. So I'll just put like a little star over here, but that star could be literally anything. And by anything I mean like any expression that will allow us to create like a power series when replaced into that on the right side. And using this idea, we can immediately answer the following question. So, for example, what would be a power series that represents this function? And the answer is very simple. If we want to find the power series that represents this function, we identify this pattern, and we identify that in order for us to take advantage of this pattern, the star has to be 2x. So that's exactly what we're going to do. We're going to replace the star with 2x. When we do that, don't forget that we also have to replace the star in the statement about the interval of convergence. So meaning that we will most likely obtain some sort of absolute value inequality that can be then solved. So in this case, this is the solution of that inequality, and therefore this is the interval of convergence for this power series that we created, and the series will converge to the function with which we have started. But anyway, so the last step here is to simplify it. And what we have learned here is that the function 1 over 1 minus 2x has the following power series representation. So I'm just going to expand the first 5 terms. So it's going to be 1 plus 2x plus 4x squared plus 8x cubed plus 16x to the 4, and etc. So similarly, we can derive power series representations for many other functions. So let's do another example really quick. So what star should be set equal to in order for us to take advantage of this pattern and come up with the power series representation for this function? The correct answer is it should be set to be negative 3x. So this is our alternating series. And of course, remember, all of this only holds on certain interval of which we call the interval of convergence. So let me just finish writing some of these elements. So when n is 0, we have 1 minus 3x plus 9x squared minus 27x cubed plus 81x to the 4 minus 243x to the power 5th, etc. So this is a power series, and this statement only makes sense on the interval described by the following inequality. Has to be less than 1, and therefore x has to be between negative 1/3 and 1/3. Now we come up with this interval of convergence analytically without doing much math. However, we can also come up with this interval of convergence by looking at this power series and setting up the ratio test. So as limit as n goes to infinity of the ratio of the nth term, n plus 1th term, over the nth term, and if we find it, we'll see that we're going to have negative 3 over here, and absolute value of x, actually sorry, the negative 3, so we're going to have the absolute value of negative 3x here, but remember the absolute value of a negative number is just the absolute value. So in this case the absolute value of negative 3 is 3. So this is what we have, and of course x could be pulled outside of the limit, and then limit of 3 is just 3 because nothing here depends on n. So the final answer is this, and this has to be less than 1 per ratio test, and we end up with the same exact inequality as before. So to find the interval of convergence, you can either use the and of course we still have to check the boundaries. I'm not going to do this right now just to save some time, but we know analytically that the boundaries are not included because of this inequality that we used, that was derived from the original identity over here. So anyway, if you don't follow this analytical approach, you can always just find the interval of convergence manually the way we did it before for any power series. Let's do another example. Let's do 1 over 1 minus x cubed. So let's find the power series representation for this function, and in this case what is star has to be set equal to, it is x cubed. So the answer is pretty obvious here, and we just have to maybe write it out a little bit in a nicer way without any parentheses, and so this is the power series for this function, and the interval of convergence can be determined by solving this inequality, the solution for which is this. So what we did is, again, we found the power series representation of this function, and we found the interval on which that is true. All right, so let's do another example. Let's maybe combine all the things that we just learned. And again, what is the star equal to, or should be set equal to, in this pattern in order for us to take advantage of this pattern and figure out the power series for this function. So maybe press the pause for a second and think about it, but the answer is negative 3x squared. And of course, to be thorough, we're gonna also set up this inequality to find the interval of convergence. Now, simplifying the expression inside of the sigma, well, we don't really have to, but it's just nice to have it written in the most simple way. So this is the power series now, and to solve this inequality, I mean, sometimes it is easy, sometimes it is not. This inequality actually leads to this quadratic inequality, and to solve this quadratic inequality, we're going to use our algebra skills. And again, we can rationalize the denominators here. Or we can just roughly estimate it by throwing it in the calculator, but again, the exact answer is preferred. So what we did is we found the power series representation of this function again, which we haven't known until now. And we also found the interval of convergence for this statement. So let's now try to learn some other patterns, or develop a technique that would allow us to recognize some other patterns. And in particular, one of the other easy patterns that we can quickly learn is something like this. So it doesn't have to be 1 over 1 minus x, but what if we have something like this? So we already know what to do when it is just 1 and 1, right? And when x is not really x, but something else. But what do we do when we don't have 1 over here or 1 over here? So how do we find the power series for a function that looks something like this? And let's do a quick example. Let's find the power series representation for this function. And the quick step that kind of solves all our issues is the following. We're going to take out 2 from the numerator and 3 from the denominator. So we're literally just going to take out 2/3 from this entire function. And now let's see what's left. So 2 from the numerator leaves us with 1, 3 from the denominator leaves us with 1 minus, and when you take out 3 from the denominator, you have to divide x by 3 as well. So now we don't have to really worry about the 2/3. It's out of the equation. We don't have an equation, but not literally equation. It's out of the picture, and we only have to worry about now this. But this has exactly the same pattern that we have been playing with for the last 15 minutes. So we know what that is equal to. So that's going to be equal to the following series, where instead of the star, I'm just going to have x over 3 as a part of the pattern. And again, we're also going to fix up the interval of convergence. We're going to keep that in mind as we're finishing up this problem. So I'm going to bring the coefficient back into the series. So we have 2/3 times x to the n over 3 to the n. And now putting things together gives me the following. We have 2 over 3 to the power n plus 1 times x to the power n. And if I want to write a couple, or let's say at least 4 or 5 first non-zero terms, it will be 2/3 plus 2/9 x plus 2 over 27x squared plus 2 over 81 x cubed, etc. So this is the power series representation of that function, and all of this makes sense only for the following values of x that are described by this inequality. So we used the pattern here, but that pattern only works when this is true. So to find the interval of convergence, we have to solve this inequality, which has a very simple solution. So there you go. So we learn how to recognize not so simple pattern and take advantage of that this identity right here. Let's do a couple more examples. So let's write a power series for this function. Just like before, I'm going to take out 4/8 And we're gonna write the power series for this next. So the star would be the negative x squared over 8. And let's simplify all of this. So of course, as I'm doing this, I'm going to remember that it only makes sense when this is true. And this is going to give a rise to my interval of convergence. But let's finish up writing out the power series. So I'm going to bring 1/2 inside of the sigma. I'm going to distribute that. All of that. We have 8 to the power n here, and we have x to the power 2n. So using my algebra skills, I guess I can rewrite this alternating series like this. So instead of 8, I'll write 2 to the power 3. So it's going to be 2 to the power 3n, and then we have another 2, so it's going to be 2 to the power 3n plus 1 times x to the power 2n. And if I had to write the first 5 terms, I would have just, I guess, expanded it. Might as well. So when n is equal to 0, we have 1/2. When n is equal to 1, we have 1/16x squared. When n is equal to 2, we have 2 to the 7. That's 128. X to the power 4. Let's do one more. When n is equal to 3, we have 2 to the power 10. And x is to the power 6. So this is what this power series looks like. And it only, this equality only makes sense, or rather this only makes sense when x is in the interval of convergence, which is defined by this inequality. Solution to which looks like this. So we found the power series for a given function. And another pattern we're going to explore in this next example. So it's going to look a lot like the original problem that we did right here. So 2 over 3 minus x. But I'm going to throw a bunch of x's in the numerator, and let's see what's going to happen. And what happens is that we can still take advantage of the pattern by kind of combining that x to the power 5 with the 2/3 that I'm factoring out from the original function, right? So it's going to look a lot like what we've done previously, but we're just going to have that extra x to the power 5 hanging over there. So this becomes, or can become, or can be written as the following power series. We've done this before, but now what do we do with that extra x to the 5th? Well, it turns out that since it doesn't depend on n, we can easily move it back into the power series, just like it was if it was a number. So if we bring it back inside, then we're going to end up with just extra 5 x's hanging in there. So basically it just shifts the coefficients down the power series by 5. So we're going to have 2 over 3 to the power n plus 1, but we're going to have, instead of x to the n, we're going to have x to the power n plus 5. So the first term of this series, when n is equal to 0, we're going to have 2/3, but instead of just being 2/3, it's going to be 2/3 x to the power 5 plus 2/9 x to the power 6 plus 2/9 x to the power 7, and so on. And it doesn't affect the presence of extra x to the power 5 doesn't affect how we find the interval of convergence, because the only thing we needed is the following inequality to be satisfied, which doesn't depend on whether you have x to the 5th or x to the 10th over there. So the solution of this inequality is x must be between -3 and 3, and this is the interval of convergence for this power series. Now we can change the direction in the way we work with this pattern. So we've been given a function. So we've been so far answering this question. We've been given a function and we're trying to figure out the series. Now we can reverse the application of this pattern, and we can start with a series and try to figure out the function. So for example, can we find, and again remember, this is not a trivial question, can we find the, I guess I should write it like this to make it a little harder to see the pattern. Can we identify which function does this power series converge to and its interval of convergence? And all there is here is to just kind of disassemble this structure and see the pattern. And it all comes with just experience of going back and forward. In this case, we like the powers of n, right? So we're just going to remove that extra 3 that hangs in there. And when we do that, here's what we have left. So you can check the work. And this power series under certain conditions, what are they? Well, the condition for this statement is that this must be less than 1 in order for what I'm about to write to hold. But if it is so if this inequality holds, then this is nothing but this function. So again, all we're doing is we're just reversing the direction in which we use the pattern, and now simplifying this and distributing that 3 over, we just found the power series. I'm sorry, we didn't found the power series, we found the limit of a power series. So we found what kind of function does this power series act like. It acts like this function. So we started with the power series and we ended with the function, and all of this, in particular this equation or equality, only makes sense when this inequality is true. So to solve this inequality, it's just a simple absolute value inequality. X must be between 3/4 and -3/4. And we answered the question, as the question was, what function does this power series acts like? And later we'll learn other patterns which will allow us to create many other relations just like this one, which in turn will allow us to create many other relations. So in reality, there are many known relations like this. So there are many functions for which we do know their power series representations, and there are many series for which we do know the functions that they converge to, but also the truth is that there are many series for which we don't know what their limits are, and it's possible to create a function for which we wouldn't know what a power series is right away. So again, we're answering some non-trivial questions here, and what we've done is called creating power series.